So what exactly does equilibrium tell us? And we're going to focus on looking at two things that equilibrium tells us. And tells us, one, the direction of the reaction. So which direction is it going to go if we start with a certain amount of our reactants and or our products? Or it tells us what our concentrations will be at equilibrium. So if we start with certain amounts of concentrations, what will we end with? Okay, so our direction of the reaction, which is what we're going to talk about in this video, is going to be looking at Q, our reaction quotient, our concentrations at equilibrium. This is going to be using ICE tables or ICE tables, and that will be what we cover on Tuesday's lecture. So for this lecture, what we're looking at is the direction of the reaction. So our reaction quotient, we give this the symbol of Q, and we're going to use concentrations with it mostly, so QC, just like Kc. It's going to be the same expression as our equilibrium constant expression, so the same thing for Kc, except we aren't going to know if we're actually at equilibrium or not. So until we know we're at equilibrium, we don't want to use Kc, we use QC instead. So it's going to be the same expression as Kc. So the purpose of QC is then once we calculate it, we'll compare it to Kc value. So if the value that we calculate for QC is greater than the value for Kc, that means that QC is too big. Okay, so too big, the numerator is too large, the products are too large. So our equilibrium, okay, or the progression of our reaction is going to shift to our reactants or shift to the left. If QC is equal to Kc, so if we calculate QC value and that value is the same as our equilibrium constant, that means that this reaction is at equilibrium. If QC, the value of it, is less than the value of our equilibrium constant, that means that QC is too small, so our our denominator is too large, so your reactants are too large, so then your reaction is going to proceed towards your products or to the right. So the question, so what this is addressing is it's looking at, okay, you're given some concentrations of your reactants in your products. Are you at equilibrium? Do you need, is the reaction still going to go in the forward direction, or is it going to go in the reverse direction? So let's look at an example like that. So we're given some moles of our starting material, and we're putting it into a 1500 milliliter flask. And we're asked, is this system at equilibrium? We know Kc for this equilibrium is 54.3. So ask yourself one question: are reactants, products, or neither favored in this reaction? So our Kc value here is greater than 1, which means that our equilibrium is going to favor our products. It's greater than 1, so we're going to favor the products. But the question is, are we favoring the products enough with our concentrations that we've been given? Well, we've been given moles, but we can convert them into concentrations. So we're going to use our reaction quotient, QC, and it has the same expression as our Kc expression. So we have our products raised to the power of their coefficients divided by the reactants raised to the power of their coefficients. So we have the concentration of Hi squared divided by the concentration of H2 times the concentration of I2. So remember, concentration, our square brackets mean molarity, so we need moles per liter. So I know my 1500 milliliters here, that's going to be 1.5 liters. So for my concentration of Hi, I'm going to have, let's see, where's Hi? I have 1.9 moles per 1.5 liters. Oops, square bracket. And that's going to be squared. And that'll be divided by my concentration of H2. So I have 0.75 moles of H2 per 1.5 liter. And then times the concentration of I2, 1.3 moles of I2 divided by 1.5 liters. So my calculator gives me 3.7. So that's my QC. 3.7 is less than 54.3. Okay, my KC. So QC is less than KC, which means that my reactants are too large. So my reaction is going to proceed to the products. So my reaction is going to go that way, towards the products. Now, some of you might be asking, well, I put this into my calculator. I didn't put this in there, and I still got the same answer. Well, in this case, you got lucky because you had 1 over, or 1.5 in the denominator here squared, and then 1.5 and 1.5 also down here. So they happen to cancel each other out in this example. Okay, depending on the stoichiometry and how this is set up, not all reactions, their volume will cancel out that way. So you want to make sure that when you plug in values into your square brackets, that you're always using molarity. Okay, in this case, it just happened to work out, but definitely make sure that you are keeping appropriate track of that.